What if the strongest muscles of the future weren't grown? What if power didn't come from flesh, bone, or metal, but from thread? Imagine a world where fabric contracts like muscle, where clothing can lift, robots can flex like living beings, prosthetic limbs can move naturally, and machines no longer rely on rigid motors, but on soft, woven strength. This is not science fiction. This is not a distant dream. This is the emerging science of knitted artificial muscle, a technology where textiles become actuators, electricity becomes motion, and fabric transforms into force. Today, we explore how knitted materials coated with electroactive compounds are redefining the way machines move, and how soft fabric may one day rival, or even surpass, biological muscle itself. For more than a century, machines have moved in the same way. Electric motors spin, gears rotate, hydraulics push, pistons pump. These systems are powerful, but they are also rigid, heavy, noisy, and fundamentally unnatural. Look at how a robot arm moves. It turns in sharp angles. It jerks between positions. It feels mechanical because it is. Now compare that to a human arm. It bends smoothly. It adapts instantly. It absorbs shock. It balances strength with delicacy. Biological muscle remains one of the most efficient, responsive, and power-dense actuators ever created. For decades, engineers have asked a critical question: how do we recreate the soft power biology without copying bone, tendon, and flesh? The answer may not lie in metal. It may lie in fabric. Knitted muscle is a soft artificial actuator, a material designed to contract, expand, bend, and produce force, much like a living muscle. But instead of being made of biological fibers, it is made of knitted or woven textile structures, elastic polymer threads, conductive fibers or metal coatings, electroactive polymers that change shape under voltage. The key difference? Instead of rotating like a motor, knitted muscle pulls. Instead of moving in rigid steps, it flows. Instead of sounding mechanical, it moves silently, like a living tissue responding to nerve signals. When electrical current is applied, the coated fibers contract, tightening the knitted loops and producing linear motion, the same fundamental motion that powers biological muscle. In simple terms, electricity goes in, fabric tightens, force comes out. Knitting isn't just an aesthetic choice, it's a mechanical advantage. Knitted structures are made of interlocking loops, and those loops can stretch in multiple directions, compress under load, distribute stress evenly, absorb shock, recover their original shape. This makes knitted fabric naturally elastic, durable, and adaptable. In biological muscle, millions of fibers contract together to generate smooth, coordinated motion. Knitted structures mimic this architecture, each tiny loop behaving like a synthetic muscle fiber. By adding electroactive coatings, materials that change size or stiffness when energized, scientists transform passive fabric into active mechanical tissue. The fabric doesn't just cover motion anymore, it creates it. The true magic lies in electroactive materials. These are polymers or conductive compounds that physically change shape when electricity flows through them. When voltage is applied, the coating expands or contracts. The fibers shorten or tighten. The knitted structure shrinks, generating force. This is similar to how muscle cells respond to nerve impulses. Electricity becomes the artificial nervous system. The textile becomes the artificial muscle. Unlike motors that spin in circles, knitted muscle produces linear contraction, the same type of movement found in arms, legs, hearts, and hands. This allows it to lift loads, bend joints, grip objects, assist human movement, mimic natural motion, and because it is soft, it can interact safely with people without the risk of crushing, snapping, or injuring. At first glance, it looks delicate. It feels like cloth. It bends like clothing. But don't be fooled. Some knitted artificial muscles can lift hundreds of times their own weight, generate high force relative to mass, contract repeatedly without fatigue, operate silently, Survive tens of thousands of motion cycles. IN laboratory demonstrations. Fabric actuators have pulled heavy loads, powered mechanical joints, and moved robotic limbs, all while remaining soft and flexible. This creates a new category of machines. Machines that feel soft, but perform strong. Traditional robots are rigid. Soft robots are different. By integrating knitted muscle, robots can crawl like worms, grip like octopus tentacles, walk with animal-like motion, handle fragile objects without damage. Soft robots can squeeze through tight spaces, adapt to unpredictable environments, and safely work alongside humans. Instead of metal arms powered by gears, they use fabric-powered limbs that flex naturally. This will transform search and rescue robotics, medical robots, industrial automation, exploration in hazardous environments. Robots no longer have to look mechanical. They can move like living creatures. For amputees, prosthetic limbs often feel heavy, rigid, and unnatural. Knitted muscle offers a new path. Imagine prosthetics that move smoothly, feel lighter, respond instantly, flex like biological limbs, reduce mechanical noise and bulk. Soft textile actuators can produce more organic movement, making artificial limbs feel more like real extensions of the body. Beyond prosthetics, knitted muscles could power wearable exosuits, garments that assist movement, enhance strength, and reduce fatigue. Clothing that helps you lift, walk longer, recover faster, and move with ease. Strength may soon be something you wear. Knitted artificial muscle also opens new frontiers in medicine. Soft actuators could enable artificial heart assist devices, muscle repair patches, soft surgical tools, dynamic implants that adjust inside the body, rehabilitation wearables that retrain movement. Because the material is soft and compliant, it can integrate with biological tissue without causing damage or irritation. Instead of rigid implants, we may one day use flexible, living-like materials that move in harmony with the body. Medicine may evolve from mechanical intervention to biomimetic partnership. Aircraft and spacecraft rely heavily on rigid components, which add weight and limit adaptability. Knitted muscle could allow wings that change shape mid-flight, deployable space structures, lightweight morphing panels, vibration-reducing adaptive surfaces. Instead of metal hinges and actuators, future vehicles could use fabric muscles to reshape themselves on demand. This could lead to improved fuel efficiency, reduced mechanical complexity, lower maintenance requirements, more resilient flight systems. The future of flight may depend not on stronger metal, but on smarter fabric. What if your clothes could do more than cover you? With knitted muscle, clothing could adjust tightness automatically, improve posture, assist athletic performance, warm or cool dynamically, provide physical therapy during daily life. Sportswear might enhance speed and endurance. Workwear might reduce injury. Everyday clothing might support mobility as we age. Fashion could become functional biomechanics, garments that don't just express identity, but enhance ability. Despite its promise, knitted muscle still faces challenges. Engineers must improve durability over long-term use, energy efficiency, manufacturing scalability, material longevity, resistance to heat, moisture, and fatigue. Electroactive coatings must become more stable, less expensive, more resistant to wear, more powerful at lower voltages. Like all transformative technologies, progress requires time, research, and refinement, but momentum is growing. Knitted muscles represent more than engineering. They challenge how we define movement, even life itself. For centuries, fabric has been passive. Now it is becoming active. For centuries, muscle belonged to biology. Now it belongs to manufacturing. We are entering an era where motion is woven, power is stitched, strength is knitted, movement is programmable. The line between organism and machine is slowly dissolving. Machines, materials, clothing. Imagine cities where robots move gently among humans, hospitals where implants flex like tissue, Homes where clothing assists daily life. Factories where machines feel more like organisms than tools. A world where soft machines replace hard mechanical systems. A world where motion is silent, structures are adaptive, and technology feels natural. This is not about replacing humans. It's about enhancing human potential, using materials inspired by life itself. In the coming decades, the strongest machines may not be forged from steel. They may be woven. Muscle will no longer be limited to biology. Movement will no longer require rigid mechanics. And fabric, once passive and decorative, may become the engine of motion. As science learns to knit power into thread, we may discover that the future of strength is not built, but stitched